Hello friends, MoNaCo here, our last lecture video in physical behavior of matter. While matter behaves in many different ways that we didn't really talk about in our lecture series here, we are focusing on the high points here. We're going to focus on kinetic molecular theory and how it's connected to what we call the gas laws. And you'll also have to be able to differentiate between real and ideal gases after this point. So we're just going to focus on the behavior of gases and how we can characterize that mathematically in this final lecture series now. So now we get to play those gases. We'll be able to predict what's going to happen if we change temperature, pressure, or volume. So if you increase the temperature on a gas, what's happening to its pressure and volume, and vice versa. So you're going to see how all of these parameters combine into one law called the combined gas law. That's what we're focusing on today. So here we go. Gases, they're all based on this theory called kinetic molecular theory. It's a model. It's not a perfect model. It is a model just like we use in our POGLs, and it's explaining the behavior of gases in terms of the motion of their particles. So the major assumptions of KMT are as follows. 1, gas particles have no volume. Asterisk, we know that's not true. So there's why it's a model. It's only used to describe this stuff, but it's not perfect in itself. The gas particles do not attract each other, meaning there's no IMFs. Again, we know that that isn't entirely true. This model is flawed, but it's suitable. The gas particles move in random, continuous motion. That I can say is probably pretty accurate to how gas actually behaves. And the fourth part is that when two gas particles collide, this is a term from physics, the collision is completely elastic, meaning there is no loss of speed before or after. So completely efficient transfer of energy when two gas particles collide. Now that's not entirely true in reality, but it's an assumption of KMT. So make those assumptions. Make sure that you know that they're assumptions and not laws, but they fit into this model as we describe behavior of gas. It's based on the idea of ideal gas. An ideal gas is theoretical and is used to predict the behavior of real gases. So we created this model that describes something that would work in the perfect laboratory conditions, and then we know that in reality it's not quite the same, but it's usable nonetheless. These assumptions are not true of real gases. Problems for real gases fitting the KMT. First of all, large molecules or atoms have higher intermolecular forces. So the bigger the gas molecule is, the more likely they're to attract to each other. Sometimes gases move slowly, it's kind of like when the temperature is low. And other times, the gas themselves have small volumes, and the more container, and a small container means more collisions. So these more collisions, the inelasticity of the collisions isn't perfect. So the problems for real gases mostly are the large volume or the large size of molecules, and that sometimes gases do move, in fact, slowly. Now, moving on a little bit. Real gases best under the following conditions. So this is how a real gas can behave like an ideal gas. 1, if there's low intermolecular forces, so non-polar gas molecules, the Hofbrinkels. 2, low pressure, so like if we take a gas molecule and put it into outer space where there is no pressure, and add a lot of heat so that we get up to a high temperature, like in the corona of our star called the sun. Small size particles. Hydrogen is the smallest, so it's very fastly moving under high temperature and low pressure. And you have an overall large volume of gas. So if we ask the question, what is the most ideal like gas on our planet, or rather in our solar system, we can say that it's probably the smallest gas molecule that there is, which is H2. And why? Because small, low IMF, and it's easily changed temperature. So those are the reasons why hydrogen gas, H2, is the most ideal gas on this planet. You can heat it up real hot, low intermolecular forces, and it's a small molecule in and of itself. I like that applied to the solar system because the corona around our sun is probably full of hydrogen gas, and it's very hot, lots of volume, and they're moving around perfectly. So the most ideal gas in our solar system is those surrounding our sun glowing red hot. Anyways, collision theory, kind of like a corollary or a sidecar to kinetic molecular theory. It says that in order for a reaction to occur, any reaction, particles must hit each other with the right amount of energy and the proper angle and position. So for anything to occur, you have to have particles smashing into each other. It's a simple idea, and we'll run into more of it in kinetics when we study that in the later unit. So now we're getting to where we want to focus on, which is the gas laws. And there are 4 gas laws that we combine into what we call the combined gas law. The first one was Avogadro's law. You might recognize that guy's name from Avogadro's constant, which was 6.02 times 10 to the, 23rd atoms, particles. That's where we get that first idea, Avogadro studied gases, and he got that idea of particles from studying the gases because he looked at different gases under the same pressure, the same volume, and the same temperature. And he said, in theory, all of these things have the same amount of gas particles. So when you ask which one has more gas particles, none. They all have the same. And that is the basis of Avogadro's original gas law, which he then used later on to calculate Avogadro's constant. Which one of these is going to be the most ideal gas? You have to look at the symbols involved. Argon, noble gas, hydrogen, and carbon dioxide. So which one's going to be the most ideal? You have to ask yourself, okay, what's the most ideal gas around? And it's a straight recall, rote memorization, H2. Explain, because smallest, lowest IMF. Okay? It's the smallest, it's the lightest, it's the lowest IMF. I gotta put that there. There we go. Last question here. Which one has the most atoms? Now this is a cool question because you have to look back to the formulas. CO2 has 3 atoms, H2 has 2 atoms, and AR has 1 atom. So which one of these has the most atoms? CO2, because there is 1 carbon and 2 oxygen. The others have fewer atoms. So that's a paying attention to details type question. The combined gas law. This is for gases only, and it involves combining Avogadro's law with 3 other laws, which we'll cover afterwards just to get you to know what they are. This is from reference table T. This is the combined gas law. P1V1 over T1 equals P2V2 over T2. Here's your definitions, what the P1s, V1s, T1s are. So pressure, volume, and temperature. So we're relating pressure to volume to temperature for a gas before and after something has changed. So that's why we use the 1 versus the 2. So you must use Kelvin degrees for this calculation in order to work. If you try and use the Celsius degrees that are given to you in some of the problems, your answers will appear to be right, but they will not actually be right. Now, sample problem number 1. Gas has a volume of 100 mil, a temperature of 20 K, and a pressure of 760 millimeters of Hg. That's a pressure unit. What will be the new volume if the temperature is changed to 40 Kelvin and the pressure to 380 millimeters of mercury? The way we solve these problems is simple. Just like Q, MC, delta T, we find our variables and we define them, and then we plug them and chug them. So P1 is the initial conditions. A gas has a volume of 100 milliliters, so that's 100, and a temperature of 20 Kelvin, and a pressure of 760 millimeters of mercury. That's the initial conditions. What will be the new volume? That's how you know it's describing the new conditions. If the temperature is changed to 40 Kelvin, the pressure to 380. So P2V2T2. Let's find out what those are. One of those is going to be X. What will be the new volume? So X will be our volume, milliliters, because we want to keep our units the same before and after. 40 Kelvin, 40.0 Kelvin. Okay, kelvins and kelvins, that matches, that's good. And 380 millimeters of mercury. That unit and that unit match. So we have all the information that we need to set up our problem. So we set up P1, V1, P1 times V1 equals T1. So we say 760 times 100 over 20 equals 380 times X that we're solving for over 40.0. And so at the end, when you solve for X, you are going to get a value in milliliters. That's what you want to see. So again, this is algebra. Solve for X by rearranging your equation. Isolating X by itself is how you solve for X. And you should get a value in milliliters. Another sample problem. Let's find our variables. That's what I'll help you do. And then you'll do the calculation here. So we always start with our P1, V1, T1, and we find them. Initial pressure. Ideally behaving gas occupies 500 mil at STP. There's our initial pressure and temperature. So 0 degrees Celsius and 1.0 atmospheres. And if that really want to be specific, it's 101.3 kPa. That is in our reference table B or C or something, the first page of our reference packet. And so we got to convert our Celsius into Kelvin. So that's 273 Kelvin in order to do this. So now we found our initial state. So we have 500 mils is our volume. Our pressure is 101.3 kPa, kilopascals. That's the normal boiling point pressure of lots of things. And then our temperature is 273 Kelvin. So this one required a little bit of footwork before you could even start it, because you had to convert STP into Kelvin and kilopascals. Now we look for our second condition, pressure 2, volume 2, and temperature 2. We say, ideally behaving gas, 500 mil at STP. What volume does it occupy? So we need to know X mils. We're going to make our units match at 546 Kelvin and 980 kPa. So that pressure is absolutely huge amount of pressure that are putting onto that material. So we set up our P1 V1 over T1. So 101.3 times 500 over 273 equals, let's see, 980 times X over 546. So you're going to solve for X, and you're going to be given milliliters for your final answer. I want to see your value. Now, thinking off the top of my head, we increase the pressure and the temperature, so it won't necessarily double or triple or something in volume. It's going to be an actual calculation you got to do. Both Avogadro's law and the kinetic molecular theory can be used to explain the relationship between pressure, temperature, and the volume of gas. And again, remember, that equation is P1 V1 over T1 equals P2 V2 over T2. So let's get into some of these other different types of ideal gas equations. This is ideal gas equation called PV equals nRT. It's designed to relate all of the parameters of a gas together. Pressure is P, V is volume, N is the number of moles, so how much stuff we're talking about. R is a universal gas constant. So don't worry about this type of calculation. It's not on our reference tables. It's not usually tested in the Regents exam or our tests, because it's more of an honors AP level calculation these days. Moving forward, you see that if you are going to relate pressure, temperature, and volume, the most important thing to know is these constant relationships, A, B, and C. Pressure decreases, volume increases. So if we reduce the pressure on a gas, it's going to get bigger. If the temperature increases, the volume increases. So if you heat up a gas, it's going to get bigger. And if the temperature increases, the pressure increases. So just think about heating up a balloon, essentially. If you heat up or cool down a balloon or squeeze a balloon or stretch a balloon, what's happening to that? So we'll cover all those as we cover the combined gas law. And these are the three laws combined with Avogadro's law that were used to create the combined gas law. And the most important thing on these slides is actually the graph. Not the name of the guy who did it, even though, you know, Boyle was a really important scientist. Boyle's law relates volume to pressure. More pressure you put on a gas, the less volume it has. That's what this graph is saying. That's an inverse relationship. If you squeeze a gas, it gets smaller. That's kind of a no-brainer, to be honest. Let's see. The next very important relationship is Charles' law. It relates volume to temperature. So if you heat up a gas, it expands. Wow, kind of like intuitive. You know, if you heat up a gas, it gets bigger. And the last, Gay-Lussac's law, is relating pressure to temperature. Now, this one isn't immediately apparent, but this is kind of how your engine is working in the car. That as you increase the pressure on a gas, the temperature increases as well. Basically, the more you squeeze a gas, the more collisions and the more friction between the molecules are in there, the more heat or temperature, well, the more temperature rises. The amount of heat that it has is kind of the same. It's just when you pressurize it, the temperature rises. Sample gas law problems to try. Again, you want to set up these types of things to find your variables. P1, V1, T1, P2, V2, T2. You got to set these up to isolate your variables and solve for the X that it's given to you. If you ask to keep something constant, I personally choose to put that as a number 1 in my equations. Gas is a volume of 75 mil. Temperature of 15 Kelvin. And a pressure of 760 millimeters of mercury. What will be the new volume? So that's X milliliters. When the temperature is changed to 40 Kelvin and the pressure is changed to 570 millimeters of mercury. All you really need to check is that your temperature is in Kelvin and that your units otherwise match. And you can go ahead and solve according to P1 V1 over T1 equals P2 V2 over T2. Okay, so that's all you have to do in these sample gas law problems is set them up by finding your variables and then plugging and chugging in to get your answer. Volume of sample of gas is 273 and 200 liters. If the volume is decreased, constant pressure. So this is a situation where we have constant pressure. So when I set these up, I think this. I set them up so that constant pressure, heck, might as well keep it at 1.0. I actually put the 1.0 into my equations. It calculates out at the end. 273 Celsius. Notice here, you're going to have to convert to Kelvin in order to do this problem. Otherwise, you're going to get the wrong answer. So that's a challenge to you. Using pressure set at constant value, find out what the new temperature of the gas is going to be. New volume of 100 ml of gas, if the Kelvin temperature and the pressure are both doubled. Kelvin temperature and the pressure are both doubled. Notice it doesn't tell you what those values are, so you can just pick any number and then double it in P2. So P1, V1, T1, P2, V2, T2. Just make sure that you double the temperature and the pressure from condition 1 to condition 2 when you solve for that particular problem. Now the last one, what temperature will the gas occupy a volume of 200 ml and have a pressure of 660 torr? This is back to the basics, back to the original P1, V1, T1. So you just set up your P1s, V1s, and T1s, and you go ahead and plug and chug and solve for your P2, V2, and T2. There's no amount of practice that's going to replace your practice pack here, so there's a lot of important stuff in the practice pack. Lots of pages of this stuff to do. Because that's the only way you're really going to understand how these calculations work. There's a quiz related to this as well as a POGL related to this material. So I'm not sorry for the long video because there's a lot of material in the gas laws. And practice, practice, practice. Thanks for watching.